All right, so in the last podcast, we talked about how to calculate the energy change for these diagonal portions of the graph, and we decided that Q equal MC delta T was the best way to go. Now, on these flat regions of the graph, we're going to have to do something else. There is no change in temperature here. So delta T would be 0. So Q equal MC delta T will not help us. Plus, we're going from one state to another. So we would have a hard time determining which specific heat value we should use. Should we use liquid water or should we use solid water? What should we use? So during a phase change, the temperature is not changing, as we just noted. But energy is still being added, okay, or removed, depending on which way you're going. This energy is not making the molecules move faster, so it's not increasing the energy or the temperature, but instead the energy is being used to either make or break the IMFs, or the intermolecular forces between the molecules. So we have two different conversion factors that will help us. The first is, I'm going to start on this side because this one really makes more sense to be first. The molar enthalpy of fusion, or the heat of fusion, is the energy required to melt 1 gram of a substance. Okay, so we're talking about going from a solid to a liquid here. Okay, so melting. It so happens that the opposite of that process of melting would be freezing, or solidification. The value for the enthalpy of fusion is the same as the value for the heat of solidification, except for one thing: it's negative. So solidification, you're talking about going from a solid to a liquid. Okay, so same exact number, except for solidification is negative because it's exothermic, you're losing energy. All right, now the other one is the heat of vaporization. Okay, so that's the energy required to vaporize, or go from liquid to gas, 1 mole. Okay, and exact same value but opposite sign would be condensation, because condensation is exothermic. Okay, so you're probably like, what this lady talking about? Well, this is what this lady's talking about. The heat of fusion, or solidification, is 335 joules for 1 gram. So it takes 335 joules to melt 1 gram of a substance, or negative 335 joules to freeze 1 gram of a substance. Heat of vaporization is 2,330 joules for 1 gram, and then condensation is going to lose 2,330 joules for every 1 gram. So just remember that condensation and solidification are going to be negative. Same number, but negative. So now let's look at a little calculations. The energy required to heat, or to vaporize, 15 grams of water. So we're starting with 15 grams of water. Vaporize, which means we're going to need the heat of vaporization. So we're just going to line up our units. We got 1 gram on bottom, 2,300 and that was 30 joules on top. The grams cancel, so it's going to take 15 times 2,330, and you should get that. So that's how many joules it's going to take. All right. How about the mass of water in grams that can be vaporized by 20 kilojoules of energy? Well, our conversion factors are in joules, not kilojoules, so we'll need to convert. So 20,000 joules is 20 kilojoules. Vaporization, so again, heat of vaporization. So we're going to use the same conversion factor, but now joules is on top. So we're going to have to flip it so that our units line up. So basically you have 20,000 divided by 2,330, which will vaporize 8.58 grams of water. All right, now the last one asks us to calculate the energy needed to freeze 3.25 moles of water. Well, we're starting in moles, so that does give us one extra step because our conversion factor is in grams. So we'll need to put the molar mass of water on top so that we can get grams, and then we can set up our conversion factor. So 1 gram will be on bottom. Now we're talking about freezing, so we're going to need the heat of fusion, but freezing is the opposite, so it's actually the heat of solidification. So this is going to be negative, right? So it's going to be negative 335 joules. And then you're going to multiply across, and you will lose 19,614.7 joules to freeze 3.25 moles of water. Okay, now I really like this picture because it kind of sums it all up for us. So it's still, remember, this is from the first podcast, so showing us our states of matter that are occurring in the molecular form at each portion of the graph. This also shows us that for the diagonals, we can use Q equal MC delta T. And then for the flat lines, we're using the enthalpies of fusion or vaporization or condensation or solidification. Okay, so I really like that because it just kind of brings it all together. All right, so this one is kind of like a big marathon example problem. So let's pretend we're going to a Japanese steakhouse. We order some hot soup and it arrives. There are 250 milliliters of it and it's at 90 degrees. Oh my gosh, it's so hot. I don't want to burn my mouth, but my stomach is really growling. So I put 3 32-gram ice cubes into the soup, and they immediately melt, and my soup becomes cooler. What's the final temperature of my soup after all my ice has melted? And we're just going to assume that the specific heat and density of the soup is the same as water. Okay, so first we are dealing with 250 milliliters. Remember, density of water is 1 gram per milliliter, so we're really talking about 250 grams here. Okay, so this is the hot soup. Okay, all right, so I'm going to set up two different little charts here. Okay, so the ice is one thing that we've got going into this, and then the soup itself is the other. Okay, so we know that the ice is going to gain energy, right? So it's going to have a positive Q, while the soup is going to lose. Okay, because the soup's going to try to transfer its energy to the ice, and eventually the ice is going to melt. We have 3 32-gram ice cubes, so 32 times 3, so our total mass of ice is 96 grams. Okay, now ice melting, we're talking about a phase change, so we're going to need to use our enthalpies of fusion. So how much energy does it take to melt 96 grams of ice? So if you just go ahead and set up your conversion factor, grams will cancel, and you will get 32,160 joules is how much energy it's going to take to melt that amount of ice. So we know that the amount of energy that the ice absorbs is the same as what the soup released or lost. Okay, so now we know our Q for our soup, but remember it's negative because our soup is going to lose energy. All right, now our soup had a different mass. It had a mass of 250 milliliters, which we figured out a while ago was 250 grams. Okay, and we know that our soup started at 90 degrees, so that's the initial temperature. Okay, so now we can set up Q equal MC delta T. Okay, so our Q is there. All right, our mass is 250. C is water, and then we're looking for our T final, and our T initial was 90. Whoopsie. There we go. Okay. All right, so now we're just going to do a little bit of math to get everything where it needs to be. So I get, and I'm going to go ahead and just change this to X at this point. Okay. All right, so that's what I get when I multiply all that side out. And then I still got my negative 32,160. I'm going to combine like terms, so I'm going to add this to the other side. Give me 61,980, and that's still equal to this. Divide to get X by itself. All right, and X is 59.25 degrees Celsius, which is your final temperature of your soup. So it cooled off a lot. Yum, yum. Now we can eat it.